Welcome to SanfordFlipMath. This is Algebra 2. We are following the Springboard curriculum for Algebra 2, doing a little work on section 4.1, which is piecewise functions. And let's get right to it. Piecewise functions, as it says, are functions defined using separate equations that are only used for specific x values. So I just want to kind of mention a couple of things, and then we'll get right into graphing, because our goal is to know how to graph a piecewise function. You might be wondering, what is a piecewise function? And before I show you, I don't want you to freak out. So basically the deal is, it's kind of like separate equations that are all going to get graphed on the same graph, and we're going to do that for specific x values, as it said. So really what we're going to do is graph an equation, and then kind of either, if you can anticipate where it starts and stops, then do that, or if not, then just graph the whole thing and then erase that part. And that's kind of what we're going to do, is graph the whole piece, then erase. So piecewise, the whole idea is it's pieces. Okay, so there's nothing really that different about what we're about to do from what we've been doing graphing equations, but to make things a little easier, we're going to kind of focus on some easy equations first, and then we'll get into the more interesting ones. Okay, so notice what it says. It says graph y equals 2 for x less than or equal to 1, and x for greater than 1. Okay, so the way I need you to think about this is, I need you to think about this like y equals 2 is one equation, and then a separate equation of y equals x. Okay, now I'm purposely trying to do easier equations to start out, so that we can focus on what's weird about piecewise. Okay, so let's think about what the graph of y equals 2 looks like. Now, if you want to think about this like y equals mx plus b, there was no x, so it's like 0x. So the slope is 0, and the y-intercept is 2. And so really, we can start at a y value of 2 on the y-axis, okay? And then I'm going to go up 0. Okay, now going up 0 means I'm not going up. And I could treat that like 0 over 1 if you'd like for the slope, or 0 over 2. It really doesn't matter, because 0 is on the top. The answer is 0. So I'm going to go up 0 and over 1. I'm going to go up 0 and over 1. That graph looks like this. Now, you may not want to write this whole line yet, like I'm doing, because I'm about to mess with you. Okay, just so you know. So this is y equals 1, or y equals 2, excuse me. Now, let me further justify that by saying, here the y value at the y-intercept is 2. Here the y value is 2. Here the y value is 2. Here the y, so watch me draw points on here. At every single point, these y values are 2. So that's why this is y equals 2. Okay, let me get rid of those extra points there. Okay, I think, oh, well, that didn't really get rid of those, did it? Okay, so now I want to focus in on this little issue right here. This says I'm really only supposed to graph this for the x values that are less than or equal to 1. So these are like conditions, okay? So x is equal to 1 here. X is really equal to 1 all the way up and down that x value, okay? Now, I'm only showing you that so that you can see what we're going to do here. After I get rid of all those little dots, there we go, and I can get rid of my arrow. Is I'm picking up the eraser, and I'm about to get rid of that. So really, all I'm graphing this for, remember, is the x values that are less than or equal to 1. Now, or equal to means I want to keep this point on the end of this. Okay, so we have just successfully graphed the first piece of this function. So I have really what's going on here is I have a big old ugly function that says, yeah, I want the y values to be 2 for these x values. I want the y values to be x for those x values. Okay, so that's kind of the gist of what's going on. Okay, let's graph y equals x. Now y equals x, this is like y equals 1x plus 0, or you remember from the parent functions that we were just looking at, these are saying this is a clean parent function for a linear equation. It goes through 0, 0. It has a slope of 1, and it has, I'm off a little bit, sorry. Okay, let's try again. and something like that. It's a little bit off, but it's not bad. Okay, so this is that line. Okay, now remember though, we have some restrictions on this. This says only graph that line when x is bigger than 1. Okay, now again, x is 1 here. X values bigger than 1 are like 2, 3, 4, 5, 6, 27, 362, 562,006, that kind of thing. Okay, so bigger than 1. Well, that means I don't want the x values less than 1. Not only that, I don't want 1 itself. So like on a number line, I'm going to put an open circle there. Okay, and this is it. You've just witnessed or successfully graphed your first piecewise function. Okay, so again, the whole idea is I have pieces. So I have this piece, y equals that, and I have this piece, y equals 2, but only for those y value or for those x values. Okay, let's do another one. Now remember, you can pause this video at any point. If you want to go back and see what just happened, you can do that. If you think you know what you're doing, what I would do is try and graph this one without me. So hit pause, and then you can check it after we do it. Okay. All right. So again, what we're going to do is graph y equals negative 2x. And then we'll go back and kind of erase what we don't want. Now, if you're doing this on paper, that's a little bit harder, especially if you're doing this in pen. So if you think that you can, start and stop this thing on a dime and know exactly where it's going to start and stop, you can do it that way. So y equals negative 2x. Now, again, this is officially, this is y equals x, a linear equation with a vertical stretch of 2 and a reflection over the x-axis. Okay, that's talking about the transformations that we were just doing. Okay, unofficially or officially from a different context, you can think of it as y equals mx plus b. So the y-intercept is 0. Okay, I put that on the graph. And the slope is negative 2. You can put that over 1. So I'm going to go down 2 over 1. Okay, and then I'm going to graph that lovely equation. Oh, that was a perfectly straight line. Good job, Mr. Sanford. Oh, thank you. All right, so something like this. Okay, now again, the condition that we're supposed to be meeting here is the x's less than 0. So that means I really only want this graph when x is less than 0. I don't want, x is 0 here on the y-axis. This is where x is 0. Every point on this line on the y-axis has an x value of 0. So what I need to do is kind of back up and erase everything that's not less than 0. So all of this stuff has to go. Okay, so there's nothing over here. I erased that stuff. Okay. So now what I have to do, now quick little note here, okay, and let me pop back to the first page. It says be especially careful at the endpoints of each piece. So what I mean by that is this particular graph is supposed to start and stop at 0. But this says only keep this graph for x is less than 0. So at 0 itself, it's not included. So I'm going to put an open circle there to show that this graph goes up to that point, but it's not going to actually touch that point. Okay, it doesn't include 0, but it includes everything to the left of it. Y equals x minus 1. Has a y-intercept of negative 1. Has a slope of 1, so it's going up 1 and over 1. Now, some of you are already saying, don't draw that other piece. Yeah, that piece. Because you know that the graph is only to the right of and including 0. Okay, so again, paying attention to the endpoints where this starts and stops, that piece starts at 0, at x equals 0, and then it includes it. Okay, we're done. That's it. Okay, again, hit pause if you need to pause. We're about 9 minutes in, 9.5 minutes in. If you need to hit pause and make a run to the fridge and whatever, do what you got to do. Come back. All right. All right. So now let's have it get a little more interesting. Again, we're talking about piecewise. So we have a piece, y equals x squared. Now you don't have to write this down separately. I just want you to, I'm trying to take it out of that scary looking notation that with the brace and all this stuff. So y equals x squared is a parabola. It has its vertex at 0, 0. Okay, we've been doing a lot of work with this kind of thing lately. Okay, and it is just the parent function. Now, this particular one, okay, let me erase a little bit of my little notage here. It says less than 0. So less than 0 is the stuff to the left of the y-axis on this side. Okay, so what we're going to do is get rid of everything that's not less than 0. Now, paying attention to the endpoints, less than is not less than or equal to. So I'm going to put an open circle here to represent that it comes close to that point, but it doesn't actually include that point. This is now y equals x. So y equals x, we just worked with this a second ago, has a y-intercept 0 and a slope of 1. So it looks like this. Okay. Now, this says we want only the stuff to the right of 0 and not including 0. So anything less than is going to go away for that graph. Now, I kind of made a mess of my stuff here at 0, 0, so let me kind of fix it. Okay, so here's the red graph. This comes in. Now, technically, this function is not defined at 0, 0 at all. So I would do an open circle for this piece also. There is nothing filling this in. Okay, now, to be very mathematical about this, or at least to clean up the little details here, either x equals 0 in this case is filled in, or it's not filled in. It's one or the other. It's not both. So let me kind of show you what I'm talking about. Let's say for a hot second here that this really said that the original problem said less than or greater than or equal to 0. Then that means I would fill in this point. What color do I fill it in? It doesn't matter, because if it's filled in, it's filled in. I'm only doing different colors so that you can keep track of what I'm doing. The colors on this graph really don't mean anything. I'm just doing it so you can keep track. So if I graph this whole thing in the same color, now it's filled in, then that's the graph. So either the point is filled in or it's not filled in. Back here at x equals 0, this was filled in, this was not filled in, just to show you that if x equals 0, then the y value was really -1 there. You would substitute it into the blue part, not the red part. Remember that all of this, graphs are a picture of a solution. So what we're doing is graphing solutions for this piecewise function, or in this case, this piecewise function. Now, if I go back to the original problem, then this thing is not filled in. And again, it doesn't matter what color it is. I'm just doing colors so you can see where the different pieces come from. Okay? All right, let's do another. I think this will be our last one. So we have y equals -x. Now, if you want to say -1x minus 2, that's good. And if you want to put that over 1, you can, because I know it's easier to track slopes when you're thinking rise and run. So y-intercept -2. Slope is down 1 and right 1. Or if you want, you could go a +1 for a rise and a -1 for a run. That's fine also. But remember, the negative, okay, I'm off. The negative is either positive, or I'm sorry, the negative is either in the top or the bottom, not both. All right, so something like that. Okay, now this says that I'm only supposed to be using this graph for x less than 1. Now there's nothing sacred about 0 and 1. They're just easy numbers to find, that's all. Okay, and it says less than, not less than or equal to, so let me erase just a tiny bit more. Okay, so that's an open circle for this graph. Okay. So now this says y equals the square root of x minus 1 and then a -3. Now, just a reminder that the parent function for this is y equals square root of x. Okay, so this is why we did 4, 3 first. This is why we did all that transformation stuff first, so that when we get to the piecewise, we know what to do. Okay, so this guy has a little point of interest. Its vertex, its starting point, its initial point, endpoint, that's the word I was looking for, at 0, 0. Now, this is going to shift right 1 and down 3. So that means the starting point is going to shift that way, and I'm going to track the rest of it from there. So, right 1, down 3, puts me at that same spot where that other point is filled in, okay? Or not filled in, sorry, the open circle. So the starting point for the square root graph is here. And then normally I go right 1 and up 1 for 1, 1. Normally I go from 0, 0, right 4 and up 2 for 4, 2. And it would look like this. Okay, now this says I'm only supposed to use this for x is greater than or equal to 1. Well, it turns out these are x's greater than or equal to 1. So I'm good. I don't have to do anything with that. Okay, now let me get rid of kind of my extra stuff so you don't sit there going, what's all that squares and rectangle stuff? Yeah, it was just to help me graph. Okay. This endpoint is it is included, so it's filled in, and that's it. We're done. Okay, so piecewise, it's kind of like a sneaky way to get you to draw 2 graphs for one problem. Kind of sneaky, huh? The real reason it's here is because when sometimes in some situations you have different equations for different parts of the graph. We will look at some of that in the next video. Okay. Well, thanks for watching. This is SanfordFlipMath. I guess we're done. Bye.